effect you can see in literal greenhouses. That's why greenhouses are hotter than the area around them. Light can come into a greenhouse, then it's going to be absorbed by things, then all of the things around us are emitting infrared radiation, so heat radiation that you can't see. That cannot pass through glass. It cannot really pass through a lot of substances in our atmosphere. CO2 is the one that is the most interesting for this case, although there are lots of other greenhouse gases that we can talk about. So sunlight comes in, some of it's absorbed by the Earth, re-emitted as infrared, only some of which can escape. And so the Earth is very sensitive to exactly how much of these infrared absorbing gases is in the atmosphere. You can see this over history. So this is data from Antarctica, where we have ice cores, and if you look at the ice, you can see the temperature that the ice formed at, and you can also see bubbles trapped of air, and you can look at the carbon concentrations in those bubbles, and you see that the temperature, the blue line, maps very well onto the red line here. So carbon dioxide is not the only determinant of Earth's temperature. You also have natural cycles, volcanoes, other types of emissions, but it's clearly the dominant one over long timescales. And that's true in Antarctica. You can also look at data from the whole planet. This is reconstructed using several different means. This is over like very long time series. So the tiny spike up there is caused by humans. The rest of this is natural. You can see that what humans have done is not really comparable to what nature has been doing for the last most of a million years here. The other thing is that the rate of this movement here is very rapid compared to the natural variations that we've seen. So here's that bit blown up, recent history. You can see through the Victorian period, there was some emissions, so there was very gradual rise of CO2 of this period and a rise of temperature, but things really sort of got kicked off after about the 60s, where you can really see a very fast rise in both CO2 and temperatures. We can track where CO2 comes from. We know that natural systems both absorb and emit large amounts of CO2. Trees obviously absorb it, soil absorbs it, the oceans absorb it, but these are almost exactly in balance. Natural systems are net absorbers of CO2, so the ocean just physically absorbs it. It doesn't necessarily process it, there's just more CO2 in the ocean causing ocean acidification, but it takes it out of the atmosphere, so it's not warming us up. Also land, so trees grow, soil absorbs more carbon as we pump carbon into the atmosphere. So that's a measurable process that we've got sort of seawaters from the Victorian period, and you can just compare the pH, and it's not the same as it is anymore. So the total emissions are stronger than what nature is absorbing, and you can track vaguely where this comes from, like is it from this city sort of scale using satellites. We also have little sensors that can detect movement from a point source, so if you've got very large single point sources, you can detect that. Generally speaking, natural sources like volcanoes do not really feature on the same level. They're like maybe 1% of total peak. So we know that this is the cause of climate change, and we know that humans cause almost all of it, possibly slightly more than all of it when you take into account what nature is doing. In the UK specifically, you can detect that almost all of the hottest days have occurred in the last few decades. And also rainfall is occurring more heavily in the UK now. The physics of this is that when it's hotter, more water evaporates, but also the hotter air can hold more moisture. So when there is a cloud that goes up higher, there's going to be more moisture in the clouds that can then fall down. So you typically have both more droughts, because the ground is being evaporated more, but also more rainfall, because the water crashes out at some point. And yeah, you can see this here, different length scales over like the period from 1900 to now. Every fraction of a degree of warming causes more of all of those processes that we've talked about so far. So you see, this is the forest fires that happened in London, close to where I lived at the time. And yeah, the likelihood of things like heat waves increases with every fraction of a degree. There's also a lot of discussion about tipping points that you might have heard. There are like particular levels beyond which systems change radically. Some of those systems, like coral reefs, we understand quite well. So we know that we are already at this point where a lot of coral reefs are simply dying and it's not clear whether they will rebuild from this. Whereas other systems, like the loss of ice from very large ice sheets, there's much more uncertainty as to whether we are at a tipping point or whether it could recover if we stabilize temperatures. They're losing ice at the moment, but whether that's irreparable or not is more disputed. Because there are so many of these different tipping points, there's not one single temperature at which all of these tipping points will tip. The best estimate is that there is not this runaway climate change point, so some temperature beyond which it's irreversible that climate change will just keep getting worse and worse. That's the best estimate, but obviously there are key points where we try and watch out for possibilities that this is happening. I got data from your local weather station with the longest time duration, which is from Heathrow, and you can see that the temperature change here is about 2.2 degrees since where the data started in 1948. So that's about 0.03 degrees per year. You can see different years obviously have more variation than the trend, but the trend is pretty clear, and you can see here all of the hottest years, again, have been in the last couple of decades. In terms of sea level rise, some sea level rise is basically locked in because the sea has not adjusted to the temperature that we are at the moment. The simple physics of water expands as it gets hot means that the fact that we've already raised over a degree means that you would expect some sea level rise. However, what we do in the future will determine how much sea level rise we see. So we've already seen, just from historical observations, like maybe 20 centimeters-ish of sea level rise. That could easily reach over a meter if we don't follow. These are like the high climate action pathway. And then if you go to a very low climate action pathway, like worse than we are currently on, you would see maybe up to 4 meters of sea level rise. So this is by 2,300. So we have some amount of sea level rise that we'll simply have to learn to live with, but we also have a lot of power to control how much of that we have to live through. And so that's the end of my talk, so you have more time to ask me questions. Human-derived greenhouse gases, of course, around 1.3 degrees warming to date. It's already causing increasing number of heat waves and extreme rainfall events, which is projected to increase substantially. It threatens specific ecosystems like coral and rainforests above threshold temperatures, but it's not always clear where those thresholds are. Warming continues until we reach CO2 balance, which is approximately net zero CO2 emissions. Depends a little bit on what the Earth does around net zero and what other emissions we emit. Air temperature approximately then stops, but the sea level rise continues for a little while, even when you reach temperature stability. Yeah.